My name is Andrea Engel, and I will be talking about type 1 error versus type 2 error in evidence-based practice. First, let's talk about null hypothesis. The null hypothesis states that there is no association between the predictor and outcome variables in the population tested. An alternative hypothesis is a proposition that there is an association between the predictor and outcome variables in the population. I'm going to go over a few more aspects in statistics in order for you to better understand type 1 error and type 2 error. So now let's talk about alpha levels. Alpha levels are a standard set by researchers that determine the findings of a real phenomenon. So the smaller an alpha level is, the more rigorous the test is, and vice versa. So an example of an alpha level would be 0.05. Next, let's talk about p-value. P-value is a probability value of an observed statistic happening due to chance. P-values are given to individual data observed in a study. Next, we'll talk about what happens when we compare p-value to the alpha level. If the p-value is less than the set alpha level, then we can reject the null hypothesis. If the p-value is greater than the set alpha level, then we fail to reject the null hypothesis. Results that fall above a set alpha level don't simply mean that there's no association. They only mean that the association observed in the sample is small compared with what could have occurred by chance alone. Now that we've gone over the different types of hypotheses, alpha level, and p-value, we can dive into type 1 and type 2 errors. This chart is a good way to understand whether or not an error has been made in research. The far left circles represent conclusions from the test performed in a study. The circles along the top represent underlying reality, which is unknown. If researchers reject the null hypothesis that they have made, but in reality the null is true, they have committed a type 1 error. If they do not reject the null hypothesis, but in reality the null is false, then they have committed a type 2 error. In general, it is best to avoid type 1 errors over type 2 errors. Here is a helpful analogy between a judge's conclusion and an investigator's conclusion in research. So a type 1 error is similar to convicting someone who, in reality, did not commit the crime. A type 2 error is similar to acquitting someone who, in reality, did commit the crime. A type 1 error is a false positive, where a type 2 error is a false negative. So why don't researchers just set alpha levels really small to avoid type 1 errors, or set them much higher to avoid type 2 errors? It's because of the relationship between alpha, which is the probability of a type 1 error, and beta, which is the probability of a type 2 error. If beta is set at 0.10, then the investigator has decided that they are willing to accept a 10% chance of missing an association. With a beta at 0.10, this would give a power of 0.90 or 90%. If researchers set a small alpha level, then it would make it very difficult to reject a null hypothesis or find any clinically significant findings, making type 2 errors very common. And a larger set alpha level would make it very easy to reject a null hypothesis, making type 1 errors very common. Ideally, alpha and beta errors would be set at 0, which would eliminate the possibility of false positives and false negatives, but in practice, this is not feasible. It's important to remember that research cannot eliminate uncertainty completely. At best, hypothesis testing is a way to quantify uncertainty, and the ways we do that is through type 1 errors, which are falsely rejecting a null hypothesis, and type 2 errors, which is falsely accepting a null hypothesis. We technically cannot prove or disprove anything by hypothesis testing.